Okay, so we are continuing on. Today we will delve into Chapter 9. And Chapter 9 is all about statistical inference for means. Or basically we are dealing now with numeric variables. Okay, so everything in Chapter 7 and Chapter 8 all dealt with categorical variables. We were dealing with proportions and categorical variables. In Chapter 9, we will be dealing with numeric variables. Okay, so let me just do a brief recap, just a review, or a recap, maybe not even a review, a recap of what we have covered so far. So far we have covered confidence intervals, for proportions, and that's with one sample. Okay, and then we covered hypothesis tests, for proportions, also with one sample. And then we've covered hypothesis tests for proportions with two samples. Okay, so that's what we've covered so far, and I guess this week we will do confidence intervals for means with one sample, and then hypothesis tests for means, one sample. Confidence intervals for means with two samples, and hypothesis tests for means with two samples. Okay. Today we'll probably get through the first two topics. Maybe just the first one. Well, I don't know. We'll see. We'll see how far we get. Okay. All right. So, all of these are listed out on the formula sheet. One thing that the formula sheet has that we did not cover is kind of the formula sheet includes confidence intervals for proportions with two samples. And this was not covered in our class. I hope no one's too heartbroken about this. But alas, I have made an editorial decision to skip it. I think life will still be okay. All right, so let's take a look here. Okay. Now, it is a lot of stuff, but if we've got a grasp on confidence intervals for proportions and hypothesis tests for proportions, all of this stuff, it's pretty much the same thinking, same logic. It's just the formulas have changed and the table has changed. Okay. All right. So let's start off with the confidence interval. For mean, and we've got one sample. Okay. And so the idea here is you look at your sample. Based on the sample, what can we say about the population? That's the idea we've always had. Okay. Look at a sample, this time we have numeric data. Look at a sample of numeric data. Okay. And now we will ask, what can we say about the population? And in this case, we are talking about the population mean. Okay. So this is a confidence interval for the population mean mu. Okay. All confidence intervals are in the form of a center plus or minus a margin of error. So the confidence interval is in the form, all confidence intervals are in this form. Center plus or minus margin of error. Okay? The center is our best guess for mu based on our sample. What would our best guess for the population mean be based on our sample? Okay, not a trick question, it's the sample mean, x bar. Okay. Sample mean, this is our best guess for mu based on our sample. And then we do plus or minus. The margin of error gets broken out into a critical value times the standard error. Okay? The critical value is a t star value, and then the standard error is s divided by the square root of n. Okay. What was the critical value when we did confidence intervals for proportions? Z star. Okay, and so this is a rule. If you're dealing with proportions, you're always dealing with z, and if you're dealing with means, you're always going to be dealing with t. Okay? Proportions go with z, means go with t. Okay? And so we will get our critical value t star from the t table. Okay? T star comes from the t table. Okay, and to decide what t star we're going to use, we need something called degrees of freedom. This is a bit of a mathematical idea. Degrees of freedom, which we will abbreviate to df. df is equal to n minus 1. It's our sample size, 1 less than our sample size. So n is our sample size minus 1. That's our degrees of freedom. We'll also need our confidence level. So let me pull up my t table. Okay. All right, so let's say we have a sample size of 12. Then I would have 11 degrees of freedom. And if I wanted a 95% confidence interval, I would go to the column where it says confidence level 95%. I would go to that column, 95%, 11 degrees of freedom, and my t star that I would use is 2.201. Okay, does that make sense for everyone? All right, so it's pretty straightforward. It's just, so, you know, example, okay, n is equal to 12, and we want 95% confidence. Then that means degrees of freedom is equal to 11, and our t star is equal to 2.201. 201. Okay. Okay, let's try out a simple example, and we'll try this out. Okay. So we'll say, I don't know. We are curious, you know, how much money people, we'll say how much cash someone has in their pockets, okay? Or how much cash someone carries on their person. Okay, so let's say we do this at UCLA. Okay, so someone here, our population will be UCLA students. Okay. All right, so somehow, I don't know how we did this, but we get a random sample of, I don't know, 60 students. All right. Random sample of 60 students, and how much money do you guys carry in your pocket at any given time? I have no idea. I'm making this up. Okay, so the average of these 60 people is, I don't know, 22 bucks. I'm making that up. Okay. And then we'll say the standard deviation of the 60 students is, I don't know, $10.50. Okay? I'm just totally making it up. All right? Okay, make a confidence interval. Make a 95% confidence interval for the mean amount of cash a student carries. Oh, okay. And so one thing you might encounter is that if you don't see your exact degrees of freedom, always round down to the one that's available in the table. Okay, so if you don't find your exact degrees of freedom, exact DF in the table, always round down. Okay, even if there's like a, so, you know, you'd get 59 degrees of freedom, use 50, okay? Let's just do this. No, don't bother with the clicker question. All right, so we're gonna have x bar plus or minus t star times s divided by the square root of n, okay? So x bar is 22, right? So I'll just go ahead and I'll kind of circle these numbers. This is x bar. 1050, this is my S. 60, this is my N, right? Okay. So I will have 22 plus or minus. Okay, so I've got N is equal to 60. My degrees of freedom will be equal to 59. We go to the table and use 50. We go to the table, we round down, we use 50 degrees of freedom. Okay, so we come to 50 degrees of freedom, 95% confidence, 50 degrees of freedom, my T is 2.009. Is it okay? 2.009. All right, so I'll have 2.009. S is going to be $10.50 divided by the square root of 60. Okay, now I have to, now I need my calculator. I got 22 plus or minus my margin of error is going to be 2.009 times 1050 divided by the square root of 60. 2.723. Okay. Right. So this says on my lower bound I have 22 minus 2.723, 19.277. And my upper bound, I'm going to have 24.723. Okay, now I would say something like, I am 95% confident that the average amount of cash a student carries is between 19.27 and 24.72. 277 is 24.723. Okay, something like that. Is that good with everybody? All right. If I took this, I'm going to just copy that last statement onto this slide. You obviously don't have to write it again. I could ask a question. I could say, do we have evidence that, you know, the average amount of cash is, we'll say, not $25. Okay? How do we answer this question? We say yes, right? Okay, 25 is not in our interval. Okay, so we have evidence that the average is not 25. Okay, we could ask, all right, I guess I'll fire up the clicker box. Do we have evidence that something is not right? Okay, so do we have evidence that the average is 20? Okay, and so I guess we'll make this a question. We'll say A is yes and B is no. Alright, did everyone have a chance to click their button? Can I click, seems like everybody, you guys are getting the hang of this. Okay, so we're gonna hit stop here. Okay, yes, alright, that is correct. Do we have evidence that the average is 20? And then the answer to that is no, okay? You know, even though 20 is inside the interval, okay? Our confidence interval never provides evidence that the mean is exactly some value, okay? Okay. Well, good. So basically, the same kinds of conclusions that we make based on proportions are the same kinds of conclusions we're making here, except we're dealing with means. And the biggest change is that we're using the t-table rather than the z, and then the formula for the standard error has changed as well. Okay, let's take a look at hypothesis tests then for means. Okay, so we'll do a hypothesis test for means based on one sample. All right, so now when we set up our hypotheses, this is going to be our first step, as always, for hypothesis tests. So our hypotheses are about the population mean mu. Okay. All right, so our null hypothesis is going to be what? Mu is equal to some value mu0. And if that's the null, then the alternative is going to be what? Mu is not equal to mu0, or mu is greater than mu0, or mu is less than mu0, right? Of course, depending on how the question is written. Okay. Step 2, we check our conditions and select alpha. The conditions, these are the same conditions. The random and independent condition, the large sample condition, and the big population condition. Okay, random and independent condition, basically the sample needs to be selected randomly. So this is the same as before. Sample needs to be selected randomly. Okay, so this is same as for proportions. Okay, how do we check the big population condition? This is the same as before. The population needs to be at least 10 times bigger than our sample. Okay. The way we check the large sample condition, this is different. Okay, this has changed. This is different. Okay. For a large sample condition, when we had categorical variables, we said you needed at least 10 successes and at least 10 failures, right? Or n times p had to be bigger than 10, and n times 1 minus p had to be bigger than 10. Okay. Now that we're dealing with a numeric variable, we don't have any successes and failures. Okay, we don't have successes and failures. So the way we check conditions, rule of thumb, and this is not always the case, but the rule of thumb is n should be greater than or equal to 25. Okay, that's kind of a rule of thumb. Another rule of thumb is, or not rule of thumb, is there's an exception to this, and that is if we know the population is unimodal and symmetric, meaning if the population looks normal, if we know the population is normal or unimodal and symmetric, smaller samples are fine. Okay, so you can have a sample size of 10, and it won't be a problem if we know the population is normal or at least unimodal and symmetric. Okay. And then, you know, in extreme cases, the rule of thumb where n is greater than or equal to 25, sometimes that's still not big enough, sometimes that's still not large enough, depending on the situation. But in most contexts, sample size greater than 25, big enough. Okay. All right, alpha, that works the same way as before. Okay. If alpha is not given, assume alpha is equal to 0.05. Okay. But we also spent Monday talking about whether in the context in which we want a large alpha or a small alpha, right? Large alpha, we want large alpha when type 1 error is not as bad as type 2. If type 2 error is worse than type 1, we would pick a large alpha. If the type 1 error is worse, then we want a small alpha. So depending on your situation, you may want a bigger or smaller alpha. But for most cases, we just assume alpha is 0.05. All right, and then we do our calculations to get our p-value. Okay, and so we start by finding the standard error. So get the standard error. The standard error is s divided by the square root of n. Okay, if you got the if you have the formula sheet, you'll see hypothesis tests means one sample. It'll tell you right there. You know, the hypothesis looks like this. The standard error is s over the square root of n. Okay, and then once you have your standard error, then you get your test statistic t. Okay, and so our t is our sample mean versus the mean that we expect, which was mu0, the value in our null hypothesis, divided by the standard error. So we use that, okay? And then look up t in the t table to get your tail area and then your p-value. All right, this is this step. This is significantly different, and I will devote the entire next slide to just doing this thing. Okay. And then once we get our p-value, okay, compare your p-value to make your, compare p-value to alpha to make your conclusion. All right, and so in this case, this is the same as before. If the p-value is greater than alpha, what does that mean? Do not reject the null hypothesis. And that means we do not have evidence for the alternative. Okay, and if the p-value is less than alpha, you do reject the null hypothesis, and you do have evidence. For the alternative. Okay. So pretty much it's the same as before, right? I'm hoping all of this feels very familiar. It's just now I've got x bars and mu's instead of p hats and p's, and we've got t's instead of z's. Okay, but using the t-table is significantly different, okay? And so let me explain how we do this. Okay. Using the t-table to get your p-value. Well, first we'll do using the t-table to get your tail area. Okay, so you'll notice at the top of the table it says right tail probability, okay? All right, so anyway, what we do is first we figure out how many degrees of freedom we have, okay? So figure out your degrees of freedom. Okay, and degrees of freedom is n minus 1. And then find where your test statistic t is, where t is in that row. Okay, and then the corresponding tail area is between the column headings. Okay, so let's just do an example. All right, so our example, let's say we have degrees of freedom equal to 5, and my t is equal to 2.94. Okay, so let me just kind of copy this this row up to 5 degrees of freedom. So this is what I have. Okay, so the only row that matters is this row for 5 degrees of freedom. I can really just delete these other rows. Okay, so this is the only row that matters. 5 degrees of freedom. My test statistic is 2.94. So I'd say 2.94 fits in between 2.571 and 3.365. Okay, therefore my corresponding tail probability, or my tail area, is between 0.025 and 0.010. Okay, so t is between these two columns, so I would just go with my right tail probability. My right tail area, or my right tail probability, is between 0.025 and 0.010. Okay, we don't know exactly what the tail area is, but we do know it's between these two values. Okay, so in general, when you use the t-table, you will almost never get an exact tail area. You're just going to say it's between these two areas. Okay, so we don't have an exact value, but that's okay. We don't have an exact value, but we know it is between 0.025 and 0.010. The only time you get an exact tail area is if your t ended up one of these values exactly. If my t ended up being exactly 2.015 with 5 degrees of freedom, then I know my tail area is exactly 0.050. Okay? Other than that, which is 99.9% of the time, you don't get one of these values exactly. You just get some value in between two columns. All right. Is that okay? If we have a negative value, then you just ignore the negative sign, but you switch the word from right to left. Okay, so let's do another example. We'll say degrees of freedom is equal to, we'll say 4, and t is equal to negative 2.3. Okay, so I'll go to 4 degrees of freedom. okay? And I say, oh, okay. I'm going to ignore the negative sign, and I'm going to say 2.3 fits right here, okay? But what I do, because I've switched it from a negative to a positive, this word becomes left. That's the switch, okay? Because the table is symmetric, so instead of having to worry about the negatives, we're just going to say this is now the left. And again, now I don't have an exact value, but I do know my left tail area is between 0.050 and 0.025. Okay, I just look at these column headings right here. Okay. Is that okay with everybody? Yeah. Okay. Let me try giving you a practice problem here, and then we'll just to make sure we got this. All right. So let's say you have degrees of freedom equal to 12, and we will say t is equal to negative 4.65. Okay, what is your corresponding tail? Okay, so we would say my, okay, so we'll start with my right tail. My right tail okay, I just want to make sure. Yeah. Okay, so so again, we have negative 4.65, and this time we're bounded only on one side. So you gotta make a judgment. Are we gonna have the tail area to be bigger than 0.001 or less than 0.001? And am I dealing with the right tail or my left tail? Okay, so so keep that in mind. You can talk with your neighbors, try to figure this out. Take a look at the column headings, see how the column headings move. Take a look at your the test statistics T. Make sure we understand this. I'll pause the video here. Whoops. Shoot. Okay, so I'll go ahead and click stop. Let's see how you guys did. Okay, and most of you guys got it, but some of us got it wrong. So let's take a look here. All right, so the correct answer is left tail is less than 0.001. All right, so let's see why this is the case. All right, so oops. We're going to the row 12 degrees of freedom, okay? So I've got 12 degrees of freedom. And we're going to see, where does 4.65 fit, right? So we look at 4.65 and we go, oh, okay, 4.65 goes over here, okay? And because it's a negative, we're going to switch this to left tail, right? So because of the negative sign, we're going to say this is the left tail probability, and we got 4.65 is out here, okay? So this means my tail, whatever it is going to be to this side of 0.001, okay? If we look at this, if we look at the areas, we notice that it is large over here, and as we go to the right, they get smaller, okay? Whereas our test statistics, they're small over here, and as they go to the right, they get bigger. So what we have is as t gets farther from 0, the amount in the tail gets smaller. Okay? So if t is bigger than the largest value, the corresponding tail area is going to be less than 0.001. Okay? So if t is larger than the last column, the tail is smaller than the last column heading. Okay, and likewise on the flip side, if your t ends up over here, okay, if t is smaller than the first column, than the value in the first column, then the tail is going to be greater than the first column heading. Okay, so let's just one more slide, and then we'll be done. Okay, and then so far we've been talking about getting our tail areas. Okay, either our right tail or our left tail, all of that, right? Okay, so the last part is going from the tail area to the p-value. Okay, so. And this all depends on the alternative. Okay, if the alternative has a greater than sign, then the p-value is equal to the right tail area. Okay? If the alternative has a less than sign, then the p-value is equal to the left tail area. And if the alternative has a not equal sign, then the p-value is equal to 2 times the tail area. Okay. Most of the time, if you have a greater than sign in the alternative, okay, usually t is positive, and you get the table gives the right tail area. Right tail area. Okay, and if the alternative has a less than sign, usually t is negative, and because of the switch, the table gives the left tail area. Okay. Sometimes you have a greater than sign and you get a negative or something. Okay. Well, in that case, it's just the left plus the right equal 1. Okay. In some odds, I'll say rarely, but possible. Okay, you need the other side. Being left or right. And in that cases, just know that the right plus the left equal 1. Okay. So, if you have the right and you need the left, do 1 minus that. If you have the left and you need the right, you can do 1 minus that. Most of the time, that's not the case, but it could happen, all right? Okay, well, we'll end there, and we'll see you guys on Friday.